Welcome to ECE 302. This is lecture 4.6 on exponential random variables. I'm Professor Stanley Chan. For today's lecture, I want to start with a very interesting example. Imagine that you are going to an airport where you see a thing called the energy efficient escalator. This escalator is not the same as a usual escalator in the sense that it has two modes of operations. The first mode is the normal operation mode. Whenever you have a pedestrian, it will just turn the motor in a normal speed. The alternative mode of the energy efficient escalator is what we call the low speed mode. This low speed mode will kick on when you have very few pedestrians coming. In particular, when there's no people coming for more than, let's say, 30 seconds, the escalator would turn into a low speed mode. Now, when you turn the escalator into a low speed mode, it is generally expected that the energy consumption will go down. Now, the question for data scientists would be, suppose I give you a profile like this. Okay, this is the profile from 6 a.m. to 11 p.m. And then the y-axis is the number of people that will arrive per minute. So let's say I give you this pattern. I actually go to the airport. I count the number of pedestrians that are using a particular escalator. So I do have the data. The question I ask would be, on average, how much energy saving that you will ever be able to obtain from this escalator. Now you may ask, how can this problem ever be related to exponential random variables? And how can this ever be related to data science problems? There are a couple reasons. First of all, this particular problem is not just limited to energy efficient escalators. You can imagine that you have electrons coming to a circuit. You have the arrival process according to a Poisson process, and then you want to measure the inter-arrival time, which is exactly what this energy efficient escalator is asking, because you're talking about the escalator would turn off after 30 seconds when no one comes. In other words, you need to measure the inter-arrival time between two pedestrians. The same model can be applied when you're looking at internet traffic, something that if you're interested in social networks, Facebook, Google, you have to monitor this internet traffic. And the arrival of two users can also be modeled according to something similar to this energy efficient escalator. Now you also will see a pattern like what I'm showing you here, where you have more people coming in the daytime, then fewer people that will come to your server in the nighttime. You also have these kind of pattern. So this energy efficient escalator is just one of the many representative examples that you can find in data science problems. And why is this related to an exponential random variable? It turns out that this t, which is the inter-arrival time between two pedestrians, is exactly the exponential random variable. So we want to ask many interesting questions for this problem, and by understanding how this problem can be solved, we will be able to model many different other problems. So that is the goal of today's lecture. We want to understand this problem as a motivation, during which we are going to look at the exponential random variables, look at their properties, and look at their examples. This is the outline of today's lecture. We are now in the middle of chapter number 4 of our course. And there are three random variables we want to discuss in our course. We have already gone through the uniform random variables in the last lecture. In today's lecture, we'll focus on exponential random variables. All right, and then these are the topics of today's lecture, some basic things. I also want to talk about the origin of this exponential random variable, which has a lot of connections with the Poisson random process, which we have discussed when we talk about the discrete random variables. Now, many people do not pay attention to this origin. They just treat the exponential random variable as one of the million random variables they can find in the textbook. I sort of think this as a different way. I think that this exponential random variable has a very strong root in the physics. It is linked to the Poisson random variables, and you can see in the Poisson random variable, there are reasons why this Poisson comes up. Same for the exponential random variables. Anything that leads to the Poisson will actually lead to the exponential. Once we understand how the exponentials are derived, where their origins are, we will be able to model a lot more problems than just knowing their formula. So that is the goal of today's lecture. To start with, I want to define the exponential random variable. The exponential random variable is given by this equation. That's the PDF of a random variable x. It has two ranges. The first part, you have this equation of lambda times e to the power minus lambda x. This is for x bigger than 0. Okay, so let's draw the diagram. So on the x-axis, I will have 0 as the cutoff point. On the right-hand side of this plot, I will have an exponentially decaying function. Okay, it has to go down. Why is it exponentially decaying? Because this is e to the power minus x. As x grows, this e to the power minus x will go down. There is a parameter lambda. Lambda will control the decay rate. So if you have a lambda here, so this is a small lambda, okay, what happens if you have a large lambda? If you have a large lambda, then you will go down like this. Okay, now let's also pay a little bit attention to the initial point. If you have a small lambda, your initial point will be here. If you have a bigger lambda, your initial point will be higher. It is very possible that the starting point will be bigger than 1, and that's allowed by the PDF. The exponential random variable is a one-parameter distribution. We can write it as exponential with a parameter lambda. Lambda defines the arrival rate of the pedestrian, the arrival rate of the electrons, the arrival rate of the internet users. So that is the parameter that defines the exponential random variable. The PDF of the exponential random variable is shown here. We have two plots drawn in MATLAB. This is when lambda equals to 5, and this curve is when lambda equals to 2. When lambda equals to 5, you can see that it decays much faster than the case where lambda equals to 2. The initial point, as I mentioned, they have two different initial points. In fact, you can show that the initial point, which is the fx at 0, is given by this equation. Just plug the 0 into x, and then you have this term going to 1, and so you have lambda. So when you have a bigger lambda, you will start off with a higher value. Relative to the lambda equals to 2, you start off with a smaller, lower value. The plot that on the right is the CDF. It's the cumulative distribution function. How do we calculate the CDF? You integrate the PDF all the way from minus infinity to this point. Okay, so now you're calculating the area under the curve of this PDF. And so if you are starting with lambda equals to 5, you will go up faster than if you're looking at the blue curve, which is lambda equals to 2, and so it rises up slower. What is the equation of the CDF? The CDF is given by this. The CDF of exponential random variable is just this integration from minus infinity all the way to x of your fx. So that's the generic definition of all random variables. For exponential in particular, you need to change the limit from minus infinity to 0, because for anything that's less than 0, you do get 0. The upper limit is x, and then here is your PDF. You plug in, you do the calculation, you get 1 minus e to the power minus x. Now, how does this equation look like? As you have seen in the previous slide, this is a monotonically increasing function. Why? Well, because when x grows, this e to the power minus x will become smaller and smaller, and therefore it will saturate towards 1. So you go up, and then it will saturate to 1. So that would be the curve. The sharpness of this rising curve depends on your lambda. If you have a smaller lambda, then you will go up slower, but eventually we still go to 1. Okay, and so now if you plug in the equation, then this is the CDF. The CDF contains two parts. The first part is that when your x is less than 0, you will get 0. When x is bigger than 0, you will get this curve. So that would be the two parts of the CDF. All right, so this is the CDF of an exponential random variable. Now, we can also talk about the mean and the variance of the exponential random variable. How do we calculate the mean? Well, the mean is expectation of x, which is the integration of your x, and then times your PDF. The PDF is lambda, times e minus lambda x, and then dx. Where should be the integration range? It has to be from 0 to this infinity. Okay, now this is the integration by part exercise, which is not too difficult. So let me show you. So this is the integration from 0 to infinity, and then you have x and then e minus lambda x. So we can do a change of variables to e minus lambda x. So we ask, what is this value? This value, when you do the differentiation, so you will have minus lambda and then e minus lambda x dx. Okay, and so what do you have left? So you have minus x that is remaining. Okay, so this is the these two are equivalent. I'm doing this integration by part. Then by integration by parts, I will have that this is equal to the limit of minus x e minus lambda x, and then I need to evaluate from 0 to infinity, and then I have to subtract the integration, and then I have 0 to infinity e minus lambda x, and then I have d of minus x. Okay, then what? Well, then you can show that the first guy, this is e to the power minus infinity. Okay, and so this will actually go to 0 very, very quickly. So the upper limit will be 0. The lower limit is that you substitute this x equals to 0, so the lower limit is also 0. So this will give you 0. And then here you have this minus, and then you have this plus. So you have plus integration from 0 to infinity, and then e minus lambda x dx. And so you can continue this calculation. Then you will have 1 over lambda, and then you have a minus e minus lambda x, and then you have this integration from 0 to infinity. Then you have that this is when x is infinity, you get 0. When x is 0, you get 1. So you have minus 1, and therefore you have 1 over lambda. Okay, so that shows you why that the expectation of x is 1 over lambda. Now, to calculate this variance, we know that the variance of x is just the expectation of x squared minus mu squared, mu being the first moment. Okay, then to calculate the second moment, it will just be integration from 0 to infinity of x squared times lambda e minus lambda x dx. So I'm not going to go through this process again. It is just the same trick of integration by part. And I think this you can do it yourself as an exercise to show that this is indeed 2 over lambda square. And then when you plug into this equation here, you have 2 over lambda square minus 1 over lambda outer square. You will be able to show that the variance is 1 over lambda square. Okay, so we have learned the basic properties of the exponential random variables. We'll talk about the PDF, the CDF, the mean, and the variance. Okay, so I want to spend the following couple minutes to go through a very important topic, which many textbooks doesn't really go into the details, which is the origin of this exponential random variable. I'm doing this, as I said in the beginning, is because I feel this is very important, because we want to model different events in a real situation, and we need to verify all these assumptions and see if they are correct or wrong. So we need to know the origin of exponential random variables. And what is the origin of the exponential random variables? The exponential random variable is the inter-arrival time between 2 consecutive Poisson events. Okay, so let me explain this. The 2 consecutive Poisson events means that you have a Poisson process. Okay, so Poisson process says what? Poisson process says that I have someone coming. Let's say I'm looking at this bus stop. There are people coming to my bus stop, and then people coming to this bus stop usually through a Poisson process, meaning that the arrival of these 2 people, they're independent. Okay, moreover, within certain period, a very short period of time, the probability that someone shows up or not, that is linearly proportional to the arrival rate. And then the third assumption of Poisson is that within a very short period of time, you have either 1, you have 0. With these 3, then assumptions made, then you know that throughout a certain period of time, then the number of people that will show up, okay, let's say you have this time t, the number of people that will show up in this interval, this n, it is a random variable, and the probability mass function of this n, which is an integer, that is given by the Poisson. So this is something that we learned when we discussed the Poisson random variable. Now, in this diagram, you can see that between 2 consecutive arrivals, there is a certain period of time. This time is denoted as this random variable t. Okay, it is a random variable because the arrival or the absence of the pedestrian, that is random. That's totally random. Okay, because your n is a random variable, and therefore the inter-arrival time is also a random variable. It turns out that this t, this random variable, is an exponential random variable. So you ask, what is the origin of the exponential random variable? The origin of the exponential random variable is the inter-arrival time of 2 consecutive Poisson events. Once you understand this principle, you'll be able to model a lot of events. Now, the second statement is also an illustration of what's going on here. It says that how much time it takes to go from m Poisson counts to m plus 1 Poisson count. Okay, so let's say here you have 2 Poisson counts, and then go to here, it would be an m plus 1 Poisson counts, and so this interval would be your inter-arrival time, and that is the exponential random variable. So we're about to derive the exponential random variable from scratch, from just the Poisson equation. I'm going to continue with this example using a bus. Okay, so imagine that you're waiting a bus, and then the people come with an arrival rate of lambda per unit time, lambda people per unit time. Thus, for the period of time t, the average number of people that arrives is lambda times t. Okay, so let me write it this way: lambda and t. Lambda is the number of people per unit time. Okay, So that could be, if you like, the unit of meter per second. Okay, so that's the arrival rate. Okay, so that is the speed of your car. Okay, and then this time is times the second. Okay, so we know that this is speed times the time that will give you the displacement. Right, so number of people per unit time times the time, that will give you the number of people. Okay, so the average number of people that arrives during this period of time t is lambda times t. Okay, so that is defined. And then we define this random variable n as number of people. Okay, so lambda times t is what? Lambda times t is the average number of people. It just says that on average, how many people will show up. It doesn't mean that on a particular instant, there are how many people. At a particular instant, the number n, we know that it is a random number. Okay, if it is deterministic, that's no problem to solve. It is a random number, and this random number is drawn according to a Poisson event. Why? This is Poisson because, as I said, the three assumptions hold. Between two, there's no other events. The arrival of these two are independent. Okay, and then the probability of these two to show up is linearly proportional to the arrival rate. So these are the three assumptions we make in the Poisson. That also holds here. And therefore, since n is a Poisson, we know the PMF of n. The PMF of n is that the probability where n equals to this small n, okay, and that is given by this number of people that will show up raised to the power n because you're looking at n, okay, and so that is your Poisson parameter. That is your Poisson parameter, and that's the number. So this equation here is just the Poisson equation. That is relating the number of people to the particular observation small n that you have during this period from 0 to t. Okay, so that is the t. Okay, so far we have done nothing about the exponential random variable. So far everything is still Poisson. If you go back the lectures to the Poisson random variable, everything remains the same. Okay, we are still talking about the non-pedestrians, and they are independent processes. Everything's the same. So now let us analyze the inter-arrival time. It's the arrival time between two consecutive people. So I'm going to define the inter-arrival time as the time between these two pedestrians. I want to find the PDF. I also want to find the CDF of this t. Because if I can find the PDF, CDF, I will know what kind of distribution it is. Okay, so now if I want to find the PDF, of course I know that, okay, the PDF would be f of capital T, that is the random variable for this interval time. Small t is the value that I'm looking at. To find this PDF, of course I need to find the CDF, okay, because the PDF can be derived by the CDF taking one derivative. Now to find this CDF, we know that the CDF is probability that t is less than or equals to t. That is the definition of CDF. And so if I can somehow find this probability, I will be able to find CDF, and then consequently, I'll be able to find the PDF. Now, how do we find this probability? Let's take the complement. Okay, so let's take the complement. The complement is that the random variable t is bigger than this value small t. What is this event? Let's take a look. This event is that the inter-arrival time is bigger than t. That is just the definition because t is defined as the inter-arrival time. When inter-arrival time is bigger than t, that means within t seconds, there will be no people showed up. Okay, so no arrival in t, because the inter-arrival time is bigger than t. Okay, between two consecutive arrivals, this is t. Okay, inter-arrival time is bigger than t That means within t seconds, there's no people showed up. So that should be pretty straightforward from here to here. When there is no people that shows up in this period of time t, that means the number n within this time t is 0. So n is the number of people. Okay, so n is 0. Now when n is 0, what happens? Well, we know that the n random variable is drawn according to Poisson. So we can plug in the Poisson equation, and then we have lambda t to the power 0 because we're looking at 0. And then you have 0 factorial times this quantity. So these things will be gone, they will go to 1. And so you will have e to the power minus lambda t. So you say, wow, what's happening here? What we are shown is that the complement event, this, which is the something related, we can see that it's pretty easy connection to this CDF here. It is somehow given by this equation. It's just fully derived from the Poisson process. There's no dark magic behind this derivation at all. Okay, we're just using all these definitions, and then we reach this result, which is e to the power minus lambda t. So you say, then what is the TDF and what is the CDF of this random variable t? That is not too hard. Okay, so let us do some quick calculation. Okay, so let's say, okay, so if your probability p, t is bigger than t, this is e minus lambda t. Okay, then what is the CDF? The CDF, which is this is the probability that t is less than small t, and this is going to be 1 minus e minus lambda t, isn't it? Right, because that is just 1 minus the probability that t is bigger than t. That's the complement. So you have 1 minus e to the power minus lambda t. So you have this one, and then so that is the CDF. What is the PDF? You take the derivatives. Okay, if you take the derivative once, you will have this lambda e to the power minus lambda t. Okay, what is it? This is exactly the exponential distribution. Okay, the PDF of exponential random variable. So we have shown that if you have a Poisson process to start with, and then you derive the inter-arrival time, you are indeed getting the exponential random variable. Okay, no dark magic, no mystery, everything is crystal clear. So we ask when to use the exponential random variable. We use the exponential random variable when we try to model a random variable of time, the inter-arrival time. And it has to be derived from the Poisson. So if Poisson doesn't work for your problem, then the inter-arrival time using exponential will become invalid, right? And that's why I emphasize so much in understanding the physics of these random variables, because in many real practical data science problems, you need to verify these assumptions. It could happen that the people or the users that come to your internet server, they do not follow this Poisson process. And consequently, if you use an exponential distribution to model them, it's invalid. Okay, and so for other problems like these, for example, Poisson photon arrival time, passenger arrival time, these, if your basic assumption about Poisson is correct, your exponential model will be correct as well. So let us go back to the energy efficient escalator. I want to derive some results with you. We have already gone through the motivation of this problem, and we have settled this problem. Let us now go into some equations of this problem. So let's say the people come to your escalator has arrival rate of lambda per unit time. So that could be, so you look at this segment, right? So this is the usage plot. So let's just look at one particular block of time. It could be in the morning, so that you have a constant lambda per unit time. And then for the period of time t, the average number of people that rise will be lambda t. Again, this is the exact same setup as what we have just derived. Let n be the number, a random variable denoting the number of people. So that's also usual, and we assume that it's Poisson. Let's assume that that's true. Then during any duration time t, the probability of observing n people would just be lambda times t to the power n divided by n factorial e minus lambda t. So that is the Poisson equation for this random variable n. Let t be the end arrival time. Then what is the probability that p bigger than t? So that is no arrival, okay, in t. Then what is this? This is the probability that n equals to 0. And so that will equal to lambda t to the power 0 divided by 0 factorial e minus lambda t. So that will give you this e minus lambda t. So you may wonder, oh, this slide seems to be exactly the same as the previous slide. Yes, you're right. This slide is exactly the same as the previous slide if you look at the derivation. Okay, there's nothing new here. And you can see that the reason why we set up all these discussions about the origin of the exponential random variable is to show that it's actually applicable to problems like these. Okay, you're still looking at the PDM, you're still looking at the PMF, you're still looking at the CDF, and you're still deriving the exact same result. And so what you can show is this: the CDF as a random variable t will be 1 minus e minus lambda t. Okay, and then when you take the derivative, the dt of your ft, you will get lambda e minus lambda t. And so that is the random variable for t. Okay, so now the interesting thing comes. You say that your escalator will turn into two modes. Okay, so one is the normal mode, and then the other one is the low speed mode. You will go into normal mode when people are continuously coming. You run into this low speed mode when no people showed up after t seconds. Okay, so let's imagine that you have two pedestrians, and then here is let me give a time. Okay, so this is the interval time t. Your escalator will be on for this period, and then since the next pedestrian does not come after several seconds, thus you will run into the low speed mode this period of time. Okay, and so you're setting a threshold here. Let's say the threshold is tau. So if t is less than tau, you are going to run the same. You're going to have this t. Okay, but if t is bigger than tau, you have a different random variable y. Okay, so this random variable y. You will turn into this distribution. So let me go back to let me talk about this diagram first, and then we'll go back to the equation. Okay, so let's say this is your exponentially decaying function. So this is your exponential random variable or t. Okay, now if you are looking at this cutoff time t, this cutoff time t, if you're less than that, then you're not going to do anything. Okay, so this is less than t, so this is going to be 0. Okay, now if this is bigger than t, then you have this t minus tau. Okay, now so what is this y? This y is the time that you will run into that time to run in low speed mode. Okay, all right. So let's go back to this diagram again. So you have two pedestrians. Okay, so the pedestrians are here, and then now if you have this time t is less than this cutoff, so this is your cutoff. If it's less than this cutoff, then your low speed mode how much time that you will go into this low speed mode, it will be exactly 0. Okay, why? Well, because if these two pedestrians are here, okay, and then your cutoff is at here. This is your time tau. Okay, and so you ask, oh, okay, what is the amount of time that you will run into this low speed mode? And there's no time that you will run into this low speed mode because these two people, they just come very, very closely together. Okay, versus if these two people, they are separated far apart, and then you set the same cutoff time tau, this is your tau, then you will have some saving here, right? Okay, so this y would denote this red area. If t is less than tau, then you have no saving. But if t is bigger than tau, then the saving that you will be able to get will be t minus tau because the total duration would be t, and then minus the tau, that would be the saving that you will be able to get. Okay, so y denotes the time to run in the low speed mode, or let me be a little bit more precise. We can say that the saving in time due to by this low speed mode. Okay, so we have defined a new random variable y, which is 0 when your actual interarrival time is less than tau, and then y is t minus tau when the interarrival time is bigger than this cutoff. Okay, so we ask if I want to calculate on average what is the saving that I will be able to get for my energy efficient escalator, then equivalently what we want to find is to find the expectation of y, because y is the saving caused by your low speed mode, and so the expectation of y will be the average saving caused by your low speed mode. This diagram it also explains what's going on here. This is your inter-arrival time distribution. It is exponentially decaying, and then we have this cutoff tau here. Whenever you have something that's less than tau, you will truncate it to 0. Okay, so you truncate it to 0, and then anything that is bigger than tau, you will leave as it is, but then you need to subtract from the tau. So we ask, what is the PDF of this random variable of y? This PDF of y can be calculated in two ways. First of all, we know that this region has been squeezed into what? This is less than tau, so we're looking at this case. Everything that is less than tau has been squeezed to this impulse of 0. Okay, so this region here, this region, the green region, has all been translated into this green impulse. The height of this impulse will be equal to the integration of from 0 to tau of your ft of t dt. That will be your impulse of the y at 0. Now, how about this portion here? This portion will just be the exact same portion, but then you just shift to the left by this amount of tau. Okay, so that will be the distribution of Fy for anything that's bigger than 0. So at least pictorially, we have been able to identify the PDF of y. Now, if you're confused, let me just recap a little bit again. Here, we're trying to find the energy saving that can be earned by this energy efficient escalator. In order to do that, we're carrying a two-step process. First of all, we're calculating the inter-arrival time statistics, which according to our derivations, that is the exponential distribution. And we know that that is lambda e minus lambda t, so that is clear. The second step is to model this cutoff process. The cutoff process is there because your escalator will turn into the low speed mode when the inter arrival time is bigger than a certain period. Okay, and that cutoff is your tau. And so you can see in this diagram, if tau is if your inter arrival time is less than tau, okay, so for example in this diagram, this is the inter arrival time, and then this is bigger than your tau. Less than tau, then there's no saving. Bigger than tau, you have some saving, which is the red area. And then the saving, this red, will translate to your y random variable. And since we want to model the energy saving, we want to calculate the expectation of y, and therefore we want to find the PDF of y. So the PDF of y is given by this expression. Okay, it will be given by this diagram. We just need to sit down and write down the equations. So it turns out that the probability of y at 0 is just that the integration, as I have said here, is the integration from 0 to tau of your ft and dt. So you can plug in the number, you can get to this result. How about for other values of y? That is just f t of t. Okay. However, you want to make a shift of by this tau. What is this shift? You are shifting this portion to the left by tau. Okay, so if you recall that if I have f of t and then I have f of t plus tau, this will be a function here, and then if I have a plus tau here, then the function will go to here. Okay, so these are the exact same function, but then here is starting at this point. Now I shift it to the starting point to the left by tau. So this is the PDF of your y. Now I'm writing a y here instead of a t because I'm looking at this y. Okay, I'm looking at this y. So it'll be y plus tau. Okay, so this is the PDF of your random variable y, and then computing the expectation will just become very straightforward. You look at the expectation of y, you break it into two cases. You have the case where y is exactly at 0, and then the case where y is bigger than 0. Exactly at 0, you get 0. Bigger than 0, you have this integral, and I will leave it as an exercise for you to just carry out the actual computation, and that's not too difficult. So how much saving that you will be able to earn, it depends on how much time that you are running in the low speed mode, and then you can calculate how much money you need to spend. Now, of course, this calculation depends on the time interval that you're looking at. If you're looking at this interval when there are a lot of people that are coming, the amount of time that you run into the low speed mode would be less relative to here, where you have very few people coming. Then you should expect to see more saving during this period of time. So in general, when you have a problem like this, you need to track the trajectory of the pattern, and then for each period of time, you calculate the energy saving, and then you integrate over the 24-hour period, and you get the overall saving. Okay, so this is a very particular demonstration example of how we can use the exponential random variable to solve something practical and real. If you do not use the exponential random variable, I'm not sure how you can solve this problem alternatively. Perhaps you can actually go to the power meter of the escalator and then measure the energy saving, but that's not feasible if you're trying to design an escalator for some public spaces. So I hope this example has increased your interest in this problem. And to summarize, let me recap a few points for this exponential random variable. The exponential random variable, as I said, it is really the random variable for inter-arrival time. We have shown the application in this escalator problem as just one demonstration, but you can imagine that anything that involves time would be also applicable for Poisson. That includes internet traffic, air traffic, congestion analysis, and so on. For cameras, there are many sensors using the time of flight mechanism, where you send a pulse to the scene and then let the pulse to come back, and then you measure the time. Many of these non-line of sight and also time of flight cameras, LiDAR sensors, or autonomous cars, they are all based on this exponential random variables, and they're extremely important topics in today's computer vision community. So you ask, when should I use exponential and when will it fail? Anything that the Poisson fails, exponential will also fail. For example, if you talk about the photon arrivals, when you have scattering processes through a turbid media, because the two photons they have been sent off or bounced off by the turbid media because of water molecules or other moving energy, for example, the turbulence, then the photons will deviate, and then you will no longer just get a pure Poisson process. In this case, the time of flight type of cameras, you cannot model it using the exponential random variables. All right. So in those situations, there are more advanced random variables that you need to take into account. The bottom line is that exponential random variables, they are great if the underlying assumptions are correct. And in most of the cases, these assumptions are approximately correct. And so you can apply the exponential random variables to model anything that involves chi. So this is the end of today's lecture. I hope you have enjoyed this lecture. It's a little bit long, but I do think that there are many important ideas that I hope you can learn. I know you will have questions, and I would encourage you to post your questions on Piazza, send me an email. There will be homework problems related to this exponential random variables. I hope you can try your best to work on these problems. Thank you very much.